I'm so very pleased to introduce Brian Yuan and Susanta Ghosh for today's joint seminar. So Brian is new faculty, well, not so new anymore, in your second year with applied computing and computer science, and Susanta Ghosh is in mechanical engineering. And Susanta, this is your second year too, right? Third year, okay. So we're really excited for these talks. The way that these work, if you haven't been to the joint talks we've given before, is that we'll have Brian give his talk, then we'll turn it over to Susanta, and then we'll do a joint Q&A afterwards, which hopefully that'll work with the hybrid format that we have going, but I'm sure we'll figure it out. So without further ado, I welcome you to watch Brian Yuan and his talk. So thanks, Brian. Take it away.
Thank you, Tim. Let me share my screen. Yeah. Okay, so yeah, good morning or good afternoon, everyone. So I'm Brian. I'm a assistant professor from College of Computing. So I hold joint appointment in applied computing and computer science department. So I'm today I will talk about our recent work on trustworthy machine learning in terms of the security, privacy, and safety. Actually, I'm teaching the machine learning course this semester in the CS department. You know, in the previous years, when we teach machine learning course, especially in the first lectures, what we want to do, the first thing we want to do actually is to motivate the student to try to let the student know how important machine learning is, how many applications can machine learning algorithm implement on, or how many areas can machine learning can be applied to. But however, I think in recent years, actually, we do not need to do this anymore. All the students are very self-motivated. Actually, the machine learning is everywhere around us. So I think most of you may already use some machine learning empowered applications. For example, you may use the face recognition when you want to take a selfie or you want to unlock your cell phone, right? And you may use some Google personal assistant applications like Siri or Google Assistant to set up daily meetings. Or you may use some Google Translation to understand a foreign language. Or you may like me, so Tesla is my dream car for now because of its self-driving features. So all of these are actually the machine learning empowered applications. And all of these just the tips of icebergs, really. So the machine learning is around us everywhere we look, touching every facet of our human existence. But when we try to deploy machine learning in our real-world applications, can we really trust machine learning? So first, I will talk about the safety. Can we really trust the prediction made by machine learning algorithm, made by machine learning models? So first, I will introduce our recent work on autonomous driving safety in adverse weather conditions. So I think I do not need to emphasize anymore on how hard we drive in the heavy snow. You know, as the team just mentioned, this is my second year. And when I came to Vision Tech, I think the first thing I know is actually how to drive in heavy snow. And actually, I still feel very challenging to drive vehicles in heavy snow, especially at night. So, and also, actually for autonomous driving, actually it's also challenging in these adverse weather conditions like heavy snow, heavy fog, heavy rain, or low light conditions. So we have seen increasing safety concerns. And most of these concerns is due to the poor perception of the sensors in adverse weather. For example, the camera may not provide reliable input in the low light conditions, or the LiDAR may be impaired in the fog and the snow due to backscatter. Okay, and one of the promising solutions to address these issues actually is that we do not rely on a single sensor. We use multiple sensors and to provide redundant detections based on multiple sensors. However, most of the existing like multimodal fusion approach actually leverage the concatenation or some weighted serve, which are not very effective in adjusting the focus of different sensors and various detection environment. So that in our recent work, actually we proposed a framework called the Global Local Attention Framework. We aim to adaptively fuse the multimodality sensing stream by calculating the weights that are assigned to each sensor stream. For example, in the global local attention framework, actually we developed a two-stage fusion. So first is we call it local attention network, which can attract pixel level weight, which means that by using this local attention network, we can derive a local attention map. So for each pixels, we want to, in this local attention map, for each pixels, we want to decide which sensor shall we rely on. For this pixel, we should think about, shall we rely on camera, or shall we rely on gated camera, or shall we rely on LiDAR? Or in another word, we want to assign different weight based on the input sensor data. And similarly, so we also derive the global attention network can help us to extract high-level features. By doing this, we kind of chop the image into different patches, and we want to extract patch level weights so that we can similarly assign the weights to each patch based on the performance of different modalities. And here's the result of our work. So we can see that compared with the single modality detection, for example, using camera, gated camera, or LiDAR, our proposed fusion model actually can detect more subtle and difficult objects, perform better than the single modality model detection. And here is the global attention map we derived in some of our data. We can find out that actually for some patches, actually we can assign higher weights to a certain sensors with better performance. So here the color, the light color for each patch indicates the higher weight we assign to a certain sensors. We can find out that based on different weather conditions, actually we can assign different weights to different areas in the image. So actually, we actually achieved, I would say, achieved better performance than most of the existing multimodal fusion model on adverse weather. So this is a great job done by my my PhD student Sakit. He did a great job in this work, and this work is also supported by the Mission Tech Research Excellence Fund. Yeah, so that's due to the time limits. Also, I will not go to the details of our work, but if you have any questions, feel free to interrupt me. Okay, and in this work, we try to solve a machine learning problem when the input data is distorted due to the poor sensor performance in the adverse weather conditions. And next, I will talk about another issues in machine learning or in trustworthy machine learning which is security. When the input data is distorted intentionally by some attackers, some hackers. So one of the widely investigated problems in this area is called the adversary examples. So the adversary examples are the input to machine learning models that attacker has intentionally designed to cause the model to make a mistake. For example, suppose we want to train a model to do a image classification. And this model is trained very well, which can classify this image as panda. Okay. But suppose we have an attacker who can intentionally generate some, we call the adversary noise. And we add this adversary noise to the original panda image. And we find out that the machine learning model will it will cause the machine model to misclassify this image. So this panda image is classified as given. However, for our human being, actually, we can see that this is still a panda image, right? So actually, this caused a very serious problem in the security problem in machine learning models. But who cares about Panda, or who cares about misclassifying Panda? So next, I will introduce our previous work, which targets our real-world application called syntax recognition. So the goal of the syntax recognition is to actually to read the text in natural things. For example, for autonomous driving system, one of the key components actually is to read the road signs for the self-driving. So if the attacker can add some noise to these road signs and then mislead the self-driving cars, that could be a serious issue, right? So that we propose a adversary attack, so which can actually generate so noise on the original image. So for this image with text, originally it can the machine learning model can predict it very correctly. So this image says imported. But if we add some noise to the original image, we derive this adversary image. Then if we let the model to predict this image, so this image will be predicted as business. So think about if your road sign is manipulated, and then it can create a serious problems in the autonomous driving system. And also we can do arbitrary modification on the image. For example, suppose our original image is a sequence of digits 24500. We can insert a digit by adding the noise. Okay, we can insert a digit into the image so that the machine learning prediction can become 294500. Okay, or we can substitute one digit, or we can just delete one digit. So actually, we can conduct arbitrary modification on the original image, just adding some noise to the image. And here, for the visualization purpose, so we kind of amplify the noise, but actually the noise is very subtle, so the human being cannot actually see these noises. Okay, and we published 2 papers about these adversary examples. And yeah, to tackle this, to generate these adversary examples against syntax recognition tasks, we actually modeled it as multitask learning task by nature. So one of the tasks actually is to make the adversary image inseparable to human, which means that we want to minimize the perturbation on the original input. We want the distance between the original input x and the adversary input x prime to be as small as possible. On the other hand, we want to mislead the machine learning model or neural network's predictions, so that the original the prediction made by the machine learning model is alpha of x. We want it classified as another label called L prime, which is not a correct label for this task, for this output. So that we want to minimize these 2 terms of the loss so that to generate the adversary examples. And very key point is that we connect these 2 laws with a parameter called lambda, which is to weigh these 2 tasks. And in the previous adversary example work, so usually people need to manually tune this lambda, which is very time consuming. And also if we want to attack some systems in real time, it's not feasible. So in our work, actually we try to generate the adversary examples. We want to optimize the adversary inputs by maximizing the Gaussian likelihood with uncertainty. So actually, we model them as a Gaussian by maximizing the Gaussian likelihood, and then we do not manually tune this lambda. Actually, we can optimize this lambda as the total optimization process. Okay, and also since the syntax recognition task is a sequential classification task, we also include like CTC laws in our objective function to tackle this syntax recognition. But yeah, so I will not go to the details about that. Okay, and so far I talked about the safety and the security issues in the existing machine learning algorithms in our recent work. Next, I will talk about some privacy issues in the trustworthy machine learning. So first, I will talk about a model stealing attack target the privacy issues on the machine learning model itself. Okay, so recent years, many cloud providers like Google, Amazon, Microsoft, IBM can provide their machine learning models as part of their cloud service. So we call it machine learning as a service. So and the normal users can query these service providers, and then the service provider can provide the predictions for these queries. For example, the user can send an image of bird to the service provider, and then the provider will provide a prediction whether this image is a bird image or a tiger image. So this type of service called machine learning as a service. And then we find out that in recent years, there's a lot of research investigating how to steal these models, how to load a functionally equivalent machine learning models. So in the model stealing attack, and the attacker actually can pretend themselves as a normal user, and then set a sequence of queries to the service provider, and then service provider can provide the prediction on the input image or input data. Then the attacker can use the queries and the prediction to create a stolen model, which have the similar function about the original machine learning model. So this is the goal of model stealing attack. So why model stealing is very important? We all know that in recent years, actually, to train machine learning model actually is very expensive. So these companies need to purchase a lot of machines, to send a lot of money to NVIDIA to purchase their GPUs. And also to hire machine learning experts is very expensive in recent years. And also we need to collect a lot of data since machine learning algorithm, most of the machine learning algorithms are data driven. So we need to collect a lot of data. We need to hire a lot of people to collect data, to annotate data. All of these are very costly. However, if we can steal the models, so first, the stolen model has a very high business value. For example, a model can be used to predict stock markets, which has very high business value. And the second, actually, we can provide the same service, but with much lower price through model stealing. So this is the reason why the model stealing is very important. And in recent work, actually, most of research use some training data or PEP data. Here we call them auxiliary data to conduct the model stealing. So the idea is the following. So the attacker will first extract some data from the auxiliary data set and then send data to the machine learning as a service API and to query the victim model. And the victim model will provide a prediction on this data, which is Y here. And then the attacker actually can use the X and Y to generate substitute models. So as long as the auxiliary data set is close to the victim model's private training data set, actually we can anticipate that actually the substitute model is very close to the victim model. In that sense, actually we steal the victim models with similar functionality. And in our recent work, we find out that there are a lot of limitations using this auxiliary data. For example, the auxiliary data is not always available due to some data protection regulation like GDPR in EU or CCPA in California, so that the auxiliary data is not always available. And also, we found out that actually the relationship is unclear between the auxiliary data and the task domain, the victim the training data, and also the quality of the auxiliary data cannot be improved. So that in our work, actually, we propose a data agnostic model stealing called ES attack, which can synthesize the data to overcome the limitation of using auxiliary data. Okay, so This work targets on the model privacy, the privacy of machine learning models. And further, let's take a look at the next work on targeting on the data privacy. So in recent years, we observed a increasing size of the state-of-the-art machine learning models, especially in these complex deep neural networks. So especially in the recent 3 years, actually, we will find out that in 2018, probably the size of the state-of-the-art machine learning model is around millions of parameters. But in like after 2020, actually, we can have some models with 100 billion parameters. That's a very huge number. And it becomes challenging for deploying all these large-scale machine learning models on some resource-constrained devices. For example, the IoT device or IOMT, the Internet of Medical Things devices. All these devices have just limited storage, battery, computational power, network bandwidth. So that recent years, people start looking at this topic called on-device machine learning. So means that how can we deploy these large-scale state-of-the-art machine learning models on these resource-constrained device? So one of the algorithms widely used in the on-device machine learning is called neural network pruning. Since that most of the machine learning algorithms or models, actually we have seen that most of them are over-parameterized. So that the idea of the neural network pruning is that we want to remove the redundant parameters from that neural network. And then we found out that by doing this, we can reduce the size of the model, we can speed up the inference on the device. And also, since most of the parameters are redundant, actually, the pruned neural network will not largely compromise the prediction accuracy. So actually, it looks very good for this neural network pruning to be used on our device machine learning. But our recent research found out that actually neural network pruning will increases the risk of data exposure. So we found out that actually the neural network pruning will disproportionately affect the pruned model's behavior for the training data and the test data, or in our case, the members and the non-members. For example, if we take a look at this graph, we will find out that this red line indicates the prediction, average prediction on the training data. And this blue line indicates the average prediction on the test data. We find out that the gap between these two is a little bit small. But after we do the neural network pruning, we will find that, so on the figure C, we'll find out that the difference between these two lines kind of increased. The gap between the training and the test data is increased. And this kind of distinct behavior between training and the test data in the pruned neural network actually facilitated a widely investigated machine learning attack called membership inference attack. So which try to identify whether a given data is used for training. So why the membership? So let me first slightly describe why the membership inference attack is important. So first, suppose we train a machine learning model to predict the type of diabetes, and then an attacker may know that, so the patient data is used for training by using this membership inference attack. Then actually the attack can infer that the patient suffers from diabetes. In this case, actually the confidential data from this patient is exposed through the machine learning models. So in this case, actually the membership inference attack exposed the confidential data. And yeah, so in our recent research, we found out that actually when we apply the neural network pruning on the machine learning models, we observed that through the using the and then when we perform membership inference attack on the pruned neural networks, we observed a higher attack accuracy, or in other words, the higher privacy risk in the pruned models. Here we invested 4 widely used neural network pruning approach, and we found out that we use different sparsities, and we found out that in most cases, the attack accuracy is higher than the original model, which is indicated in this black line. So that to mitigate this issue, actually, we propose a defense called a pair-based posterior balance defense. So I will not introduce the detail, but the idea is that so the pruning makes the difference between training and the test data larger. So our goal for this defense actually is to make it smaller again. So we want to mitigate the distant prediction behaviors between the training and the test data. So, and its work is just recently being accepted by Unix Security 2022, which is the top 4 security conference in the area, and also supported by NSF SHF grant. So yeah, so let me so here's the takeaway. So in today's talk, we discussed the safety issues in the autonomous driving. We talk about the several examples regarding the security issues in machine learning. And we talk about 2 privacy-related attacks, the model stealing attacks, membership inference attacks. And actually, there are many other attacks we don't have time to cover in this talk, but actually we have identified many attacks in recent years. And also we find out that the existing machine learning algorithm also exists in other issues regarding the trustworthy machine learning. For example, the misuse of machine learning, such as the deep fake, which is a big threat in recent years, right? And also the fairness, ethical issues about machine learning, and also machine learning expandability is also a very hard and a big threat when we use the machine learning, and also there are many other more issues. So that when we consider the using machine learning applications or deploy machine learning applications, so maybe we should not only consider prediction performance like accuracy as the only matrix. We may consider many other important aspects when we deploy the machine learning applications. And on the other side, actually we find out that today we talk about many issues in machine learning, and for some issues, for some threats, we provide solutions. But for many other threats, actually we find out that there's still an open question to how to solve these threats. So that actually the effective solutions are urgently needed, especially in these safety critical applications. And also here, I mean, not just the technology, the algorithm, we need to improve the machine learning algorithm. Also, we need something beyond technology, like the policy or the regulations that can make the machine learning much better in the future. Okay, so that's pretty much about my talk. So last, I will just stop at this slide. So in this talk, I cover the security, privacy, and the machine learning topics in my research, and also my research and also expand the field of cloud computing and edge computing. So we have multiple research assistants openings in my lab if you are interested in these topics, and also any collaborations are most welcome. Okay, thank you for your time.
Thank you, Brian. All right, up next we have Susanta Ghosh.
Hello, everyone. Thanks to team for nice introduction. I'm Susanta Ghosh, and I'm going to talk about application of Bayesian neural network for breast cancer image classification, especially histopathological image classification. And this is the work done by 2 graduate students, Computational and Pushkar. Here, and I worked with them. I come from a physics model-based, physics-based modeling background, like PDE-based modeling, like finite element, finite difference, or spectral methods for continuum physics problem. All right, so especially for nanomaterials and things like that. So we are venturing into applications of machine learning in various ways. So this is one such example. All right, so this is the overview of the talk. So I will briefly discuss about the breast cancer and histopathology, and then we'll talk about neural networks and its use to detect human breast cancer, especially for image classification. So breast cancer is very prevalent among women, and it has high mortality rate, and it's a devastating disease for a patient. And histopathology is a gold standard to detect whether the tumor is carcinogenic or not. And for that, this is the standard workflow for getting the histopathology microscopy images. And then a pathologist looks at these images and identifies whether these are carcinogenic or healthy. Okay, so we are trying to do that job using convolutional neural networks. Okay, so there are a lot of works in this direction, because image classification is a big area for machine learning application. Towards this, convolutional neural networks, very large convolutional neural networks like deterministic networks are very popular for various medical image classification. But as you know that these networks sometimes suffer from overfitting, or if you want to regularize, manual intervention is required, and it cannot quantify uncertainty due to its deterministic parameters, weights and biases. So here is the example of deterministic neural network. You can see that the weights and biases are deterministic values, what you obtain after optimization. Whereas in the probabilistic neural network, these weights and biases are characterized by are stochastics and characterized by their probability densities. Right? Towards this, Bayesian neural network is one of the most promising, which promises to eliminate overfitting, and you can naturally provide uncertainty quantification due to stochastic parameters, and it promises to alleviate many other things, but it also suffers from false negative quite a lot, not as much as a deterministic CNN, but still there is a lot of scope for improvement. And we explored the Bayesian CNNs using histopathology images, and we try to improve, we try to explain its how it works. Okay, that's what I'm going to talk about. This is another example or schematics of the deterministic versus Bayesian convolutional neural network. As you can see in the deterministic network, the filters are output filters basically final give you deterministic values, right? Whereas in the Bayesian neural network, these filters are probabilistic, identified by their probability density function, right? So next, how do you identify these parameters, probabilistic parameters? Two popular point estimates, that means when you get a number, are the maximum likelihood estimate, which basically maximizes the probability of observing the data D and identifies the parameters W that maximizes the probability of observing the data at hand. That's very popular, but you get a deterministic value or point estimate. Whereas in maximum a posteriori, you assume that W is a stochastic, or the parameters of this Bayesian neural network is stochastic, but what you identify is the mode of the probability density, or the maximum value of this probability density. Basically, it maximizes the posterior probability of the weights and biases after observing the data. Okay, it's like throwing away rest of the values in the probability distribution of W. You are just taking only one thing. So total Bayesian approach, or complete Bayesian approach, or fully Bayesian approach basically takes care of the entire probability, posterior probability distribution of W, and it marginalizes over the entire all possible W's basically. That means basically you are considering all possible neural network that you can have and marginalize over the parameter space given by W to obtain the to obtain the prediction Y for a given input X. That means once again, for a given input testing data, what is your output Y given the set of training data D is given by marginalizing over the parameter space. That's the total Bayesian approach. It basically, in a intuitive way, it basically gives you a prediction by considering an ensemble average of all possible neural networks. Okay, that way it automatically regularizes. That's what we see in this particular data. And how do you obtain this posterior probability of W is through the Bayes rule is very standard. We can try with some prior probability of W, and then after observing the data, you obtain the posterior probability of W. But the problem is due to this denominator, which is basically integral of the numerator over W, is intractable because our W or the parameters of the neural networks are millions, huge, right? So how do you obtain that? Basically, we assume a tractable posterior probability and then try to bring it close to P through the dissimilarity function like KL divergence, okay? Here, we assume a known model, known probability density called variational distribution. The name variation is very attractive to me because I come from finite element community, which is built on variational calculus. So basically, you are identifying the best function or probability distribution that that best probability distribution that satisfies this criteria. That means it brings it towards the posterior probability. Okay, so I assume some non-Q, non-probability distribution called variational distribution and try to bring it close to the posterior distribution of P. And how do you do that? You basically minimize their dissimilarity, and dissimilarity is identified by divergence terms like KL divergence, and which has to be minimized here, this term, and you have to identify the parameters of your assumed probability density, theta. So once you minimize this, you find the theta. That means you find a theta that let you approximate the posterior probability. And once you found the posterior probability, then you basically go back here, plug in here, posterior probability of W, marginalize this, use this prediction. Now you have a prediction which considers all possible neural networks. That's the whole idea in Bayesian neural network. And I will just briefly touch upon one thing, that this is the term that you have to minimize in this slide. The minimization of the KL term is that, and in the Monte Carlo technique, we basically evaluate this integrand for various, by drawing various samples from the assumed probability density, right? And this is the optimization steps towards that. These are the optimization steps. You reparameterize the W through a standard Gaussian standard normal process through the two parameters, mean and the standard deviation. So basically, W is a Gaussian with mean mu and standard deviation rho, and these are your parameter space. For each and every weight and bias, now parameterized by a stochastic variable, W follows Gaussian distribution with mean mu and standard deviation rho. And now if I can find mu and rho, I know that probabilistic weights and bias or probabilistic parameter for the neural network. Our objective is to find the theta for each and every weights and bias. That's it. And towards that, we basically draw samples from this W, from this probability density of W, and evaluate this function here, the variational free energy, evaluate that, and then standard technique, you take the conjugate gradient to obtain the gradient, update the parameter in the conjugate gradient. This is the standard technique, and you find the optimal value of theta. That means basically you minimize this function, the dissimilarity between your assumed probability distribution and the true posterior probability that should come after observing the data, right? So with that view, once you obtain the posterior probability, as I said, you marginalize, come up with the prediction y, but y is also probabilistic. Since y is also probabilistic, it has mean and standard deviation. Its standard deviation naturally gives you the uncertainty in your prediction. So that means not only you say this is my prediction, this image is cat's image, you also give how much confident you are. I'm 95% confident. So that's the benefit of having Bayesian neural network. Note that for a deterministic neural network, doing such uncertainty quantification is infeasible because you have to then do a Monte Carlo sampling in million dimension, right? So Bayesian neural network gives you a power to naturally come up with uncertainty. Okay, these all are existing technique. What we did is basically in the standard Bayesian CNN, the activation functions are deterministic. We identified that and we came up a way to make it stochastic. So we added a probabilistic hyperparameter alpha in its activation function. Say activation function is sigmoid, and then for various values of alpha, based on the data, it can automatically choose the best or the most probable hyperparameter alpha based on that data. So we basically extended the Bayesian CNN to have a stochastic adaptive activation function. The function is not only adaptive, that adapts to the data, it can take any of these shape. It also is stochastic. That means it obtained the predict through an ensemble. Okay, so with that, here is the update that you need to do because you have an additional parameter in addition to weights and biases. And so you have to change the loss function that we did and implemented in the code. And then now we are going to the results where we compare the deterministic CNN, Bayesian CNN, and our modification on Bayesian CNN. Okay, so this is the data set that is publicly available. It is benchmark data set where you have this type of images. These are the size of images and the size of the data set. Okay, and then we try a standard transfer learning CNN, say standard VGG 16, which is widely used for histopathological data. So we wanted to compare against this one because it is widely used. And when we do that, we see that the VGG 16 actually does very good job, but it suffers from overfitting. But Bayesian neural network, standard Bayesian neural network does not suffer from overfitting even after 300 epoch. And our proposed modified Bayesian neural network, Bayesian convolutional neural network does not suffer from lack of regularization or overfitting. So this is a great advantage of Bayesian neural network. At least for the histopathological data, we can see from the numerical results. Okay, this is an example how the neural network learns, or we take a particular weight and trace it. So we see that initially, and at 0th epoch, it has a wide range. This is the this is the initial distribution. Okay, and then slowly it gains confidence and is moved through the larger number of epoch, and its standard deviation reduces. So network becomes more and more confident about its prediction by reducing standard deviation. So here are some results, and we can see that the conclusion is that compared to the deterministic neural network, both Bayesian CNN and modified Bayesian CNN perform somewhat better, 1% or 2%, and in all performance metric, not only in accuracy, but where it significantly perform better is predicting, reducing the false negative and reducing the false positive. Here you can see that Bayesian neural network, Bayesian CNN, reduces the false negative and false positive by 11% and 7% respectively compared to deterministic CNN. And despite having only about 1.5% of its total number of parameters, the CNN has 134 million parameter, whereas the Bayesian CNN we used is 1.86 million parameters. And the modified Bayesian CNN that we propose reduces the false negative and false positive prediction even by 3% compared to Bayesian CNN. So modified Bayesian CNN has some merit. So adaptive stochastic activation function that we used gives us at least 3% improvement and by reducing the false positive and false negative this thing. And this result is reported, and all the details are published in this paper. If you want, you can take a look at it. And now we say that, okay, based on the uncertainty on our confidence on the prediction, if we divide the data on the two parts, suppose I say that, okay, when the uncertainty is 0.6, normalized aleatoric uncertainty or epistemic, both perform the same way. If the uncertainty is 0.6, then I divide the data on which my performance or the prediction confidence is very high. That means the uncertainty is less than 0.6, and some part where the uncertainty is greater than 0.6. Okay, then I see on the two data set where the data where the uncertainty is less than 0.6 is about 77%. And on that high confidence data where the uncertainty is less than 0.6, I see the accuracy jumps to 94%. So 6% improvement on a subset of data, 77% test data where the model has lower uncertainty. And we can see that this is a massive improvement. 6% improvement on a subset is a significant improvement. We see that the accuracy increases as the uncertainty threshold reduced, right? So we see a strong correlation with the model's ability to accurately predict with its confidence, right? Why it is so? We see that also the number of false prediction decreases as the uncertainty threshold decreases. Why it is so? To study that further, these are some example of the model's prediction. I have to skip that, sorry. To study that further, we try to explain this uncertainty, how the model understands that. So what we did is basically projected this data, the images, into three-dimensional, lower dimension by using a nonlinear dimensionality reduction technique called TNNLS, stochastic neighborhood embedding technique. And through that, we see that on the low uncertainty, where the model is confident, it can separate the blue healthy data from the red malignant data very easily. It's a very nice line of separation it can draw. So we see that only using three feature model can separate these into two different classes. That's why it is so accurate on low uncertainty. But that reduces, that separation reduces in medium uncertainty and vanishes in low uncertainty. So this is our kind of intuitive explanation why the model shows a correlation in accuracy and uncertainty. Okay, so this is TSNE detail. I'll skip. These are the detail of computational time and memory. And I'll come to the conclusion that we show that quantifying uncertainty is possible using Bayesian CNN. And we explain the uncertainty in the prediction. That means a strong correlation between accuracy and confidence that we try to show it visually by projecting the data in low dimension through nonlinear dimensionality reduction. And we utilize the uncertainty to create a subset on which the model is confident. And we see the model dramatically improves its performance when we focus only on that subset. And the rest of the data we can refer to human expert, or we can do for further analysis, right? So, and we have added a stochastic adaptive activation to Bayesian CNN that somewhat performs better than the Bayesian CNN. and Bayesian approach eliminates overfitting. More detail are given here in this paper. With that, I would like to thank everyone for your attention. This is a great pleasure to present here. I would like to thank Gautam and Brian, who helped us with the GPU and high performance computing, and also the funding agencies and etc. Thank you for your attention. If you have any question for me or Brian, just specify the name of the speaker so we can identify. So yeah, please go ahead.
So I'm curious about the claim that these Bayesian networks eliminate overfitting, because overfitting, in other words, is just that you have high variance in your model learning, that as you change the training data, your model changes, quite a bit, that it's fitting too much to the training data. So maybe could you give like just a brief explanation of why? I mean, I would think that no matter what learning algorithm you have, that there are cases where you're going to have overfitting, because you only have access to so much data and you don't have access to infinite data. So there's going to be variance in the model regardless.
That's kind of true, but like what I would like to point out that since the parameter is stochastic, it's drawing from an ensemble, drawing from a probability distribution. So basically, I am thinking like it's a collection of neural network that it is drawing from, so to predict, instead of a single network that is trying to fit the observed data the best. That would be my explanation for that. And yeah, we see this here, but truly speaking, other than the numerical result, I don't have a mathematical proof that it will definitely reduce the difference between training and testing accuracy. So in this case, we see that, and our explanation is that since it's a stochastic parameter that represents an ensemble, and its prediction is the mean of that ensemble.
So do you think that you can achieve the same result with regularization learning? Because when it really comes down to it, if you only have access to the data that you do, the only way to truly reduce variance from some optimum model is to have a priori information that you build into your model.
Yep.
It's a better model for the overall process. So I mean, is there some way that you can say, well, you can do the same thing with the CNN, but you have to regularize in a certain way that you can do it with the Bayesian network?
Of course, regularization helps, right? And it is a sure proven technique. There are several techniques people use. In this case, also we have regularization in transfer learning CNN. I think we had weight decay, right? I think we had weight decay. So that helps, but I don't know why. What should be a I mean, like the best regularization that will work for all the cases. Generally, from literature, we learned that weight decay works almost all the cases. It helps alleviate, and other type of regularization that we use for other problems like or L1, L2, or elastic net, or I don't know. So truly speaking, I don't have a clear answer for a unique hands-off regularization technique that will work for all sorts of data.
Yeah, well, we should talk more after.
If I can just add, so as long as the prior to the Bayesian network is Gaussian, you can have an L2 regularization for CNN that will give you an equal performance to Bayesian network. Okay. And yeah, so it largely depends on the prior and the type of parameter that you're going to choose. So if I change the prior to be, say, something else, then I'll have to find another regularization technique to make it equal to.
Okay.
So
the left side was based on PCC, right? So is the right side also based on PCC? So what was the relationship between, BCC and, because like, BCC is a type of CNN, but I'm not sure what type of architecture you're using.
Yeah, thank you.
Okay.
So I can, so the CNN architecture was this. That's a deterministic that was used here. And the Bayesian CNN architecture was somewhat different than this. Of course, it has much, much less, only 2% of the parameter of this one. Here, I have like about 130 million parameters. But the Bayesian neural networks has only like about 2 million parameters. Okay, exact architecture's image I don't have. Maybe my student can describe.
Yeah, that's fine. I think I can find it.
Yeah, all right, thank you. Any other questions for me or Brian?
Susanta, I have a follow-up question for you. Yeah, so how do you compare the Bayesian neural network with ensemble learning? Because it seems like you are trying to learn a set of neural networks sort of in the Bayesian neural network.
Yeah. So we did not compare with anything other than the transfer learning deterministic transfer learning like this type of networks, but maybe it will be a good idea to compare with other type of ensembles, right? So we did not do that. Sorry.
Okay, thank you.
Any other questions? Yes.
Yeah,
you
hello, Dr. Ryan. So I saw your model which deals with autonomous driving in adversarial weather conditions, and you showed that it basically takes some weighted average of predictions from 2 or 3 systems like LiDAR and camera. Considering that it is a real-time inference system, so I'm just curious that how much more time does your model take to draw inference, because it has to draw inference from LiDAR, then it has to draw inference from camera and do the weighted average and predict.
Okay,
So,
yes. Thank you. Let me just quickly share my screen about this architecture. And actually, so first, in our work, we didn't consider the efficiency of the multimodal fusion, because our the target is to how to improve the detection performance in this system. So we didn't actually test the inference time. But actually, our neural network design actually is pretty lightweight. So you can see that we just add two blocks before the local attention map, and then 2 blocks of the global attention map. And the rest of block are actually similar. We follow the standard object detection framework, the fast RCN. So besides this kind of 11 blocks, actually we do not add additional cost, especially the computational cost on the model. So I don't think actually our model fusion design will actually cost too much computational, the time in the inference time.
okay. Thank you.
Thank you.
So is there any other question? If there is no other question, we would thank Brian, and we'll end the session here, perhaps. Amanda?
Thank you, Susanta. Thank you for
Thank you, Brian.
organizing this.
Yeah, thanks both. If there's no other questions, yeah, I will end the session, and then this recording will also be available if anyone wants to access it later, or if you know of any colleagues that weren't able to come today too.
Thank you, Amanda.
All right, thanks so much. Have a great evening, everyone.
Have a good weekend.
Thanks,
Bye.
you too. Bye.